Assalamu alaikum. My name is Tanuja Binte Said Kotha, and today I'll be presenting a project titled Digital Parking Control System. This project helps tracks down how many cars are parked in a lot with a capacity of up to 10 vehicles using digital logic components like D flip-flops, a 4-bit comparator and 555 timers. According to my student ID, the parking lot can hold up to maximum 10 cars. In this diagram, it shows a digital parking system with max of 10 cars. First of all, a keypad sends input to the encoder. The signal controls an up-down D flip-flop, which counts car in and out. Counters and a 4-bit comparator track the total cars. When full, timer 1 triggers a full display. When space is available, timer 2 shows available. It's a simple system to manage parking using basic digital logic. This flowchart shows how a parking system tracks a car entry and exit. It starts with a sensor detecting a car. If a car enters, the system increments the counter. If a car exits, it decrements the counter. The system checks if the counter has reached 10. If count is equals to 10, it displays full. If less than 10, it shows available. Then the process ends and waits for the next sensor input. We used a 4-bit synchronous counter made with D flip-flops because 4-bit can represent values from 0 to 15, but we only need to count from 0 to 10, so we built a mod 11 counter. We derived the equation for each D flip-flop based on current state and the up-down signal. Here are the simplified expressions in the slide. All flip-flops are driven by the same clock signal, making the synchronous counter. When the count reaches 10, we trigger a 555 timer in monostable mode to display full. We derive the values. R1 is equals to 388 ohms, R2 is equals to 2210 ohms, and we considered C1 is equals to 50 microfarad. From this we get T is equals to 90 millisecond. When there's space available, we blink the space available sign using another 555 timer in a stable mode. Our goal was a duty cycle of 54% with TH is equals to 90 millisecond and TL is equal to 76.6628 millisecond. Using the standard 555 formula, we selected the same R1, R2 and R1 values. This gave us a blinking rate of amount 3.13 Hz, just fast enough to catch the attention. To manage the blinking display more accurately, we designed a simple finite state machine. Here is the state diagram and the table for the FSM designed to display blinking. In this slide, I presented the Verilog code for our FSM. It's a very simple module that updates the state every clock cycle and outputs either A or B depending on which state we are in. This system has some limitations. First, it can count only up to 15 cars, which is not enough for big parking lots. Second, it has no memory backup, so if power goes off, all data is lost. Third, the blinking display may stop working if 555 timer or capacitors fail. And lastly, there is no protection from hardware damage. Some ways we can improve the system are: first, we can use a microcontroller for better control and accuracy. Second, add memory storage to keep data safe during power loss. Third, use a stable power supply to avoid sudden shutdowns. Fourth, replace the D flip-flop with JK flip-flops for better counting. And finally, add a display decoder for clear number output. These changes will make the system more reliable and efficient. The impact of our improved system are: first, using more bits and flip-flops make the circuit larger and more complex. Second, adding a microcontroller improves accuracy and makes control easier. Third, more components mean high power uses and increased cost. Fourth, software-based systems are more flexible and reliable. And finally, using JK flip-flops helps everything work with sync with the same clock. In summary, we successfully built a Mod 11 digital parking system using DA flip-flop counters, 555 timer circuits, and a simple but effective FSM and Verilog code. This system tracks the number of parked cars and controls the display to guide drivers. It's a practical use of digital electronics. Thank you so much for watching. I hope this presentation gave you a clear understanding of how the system is built and how it works.